Hello and welcome to my original research presentation on the set cover problem, a hybrid genetic algorithm and wisdom of artificial crowds approach. First, we'll start by discussing a little bit about what the set cover problem actually is. So the set cover problem was proved to be NP-complete back in 1972, and it's a subset actually of the broader cover problems. So we can define the set cover problem by first a universe U that includes n elements, and that's such that U is equal to the set of 1 to incrementally going up to the number n, and a set S of subsets such that S is comprised of sets S1, S2, all the way up to some number S sub I. And the goal of this problem is to find a subset of S such that the elements of each subset cover or contain a maximum number of the elements in the universe. While maximizing the coverage, the algorithm needs to minimize the total number of subsets used. Here you can see a more formal definition of the set cover problem. As we discussed before, we have the universe U being an incremental set of elements from 1 up to n, and the set S of subsets from S sub 1 up to S sub I. And then down at the bottom here you can see that we have our formally defined goal state, which is maximizing U, which is the subset of covered elements in U, and the minimum of S, which is a minimal subset of selected elements from S. Let's go over a short and very simple example of the set cover optimization problem, which is what we're going to be solving in this presentation. So the set cover optimization problem is NP-hard. So let's define our universe as the elements 1, 2, 3, 4, and 5. Then we can define our set of subsets as the set 1, 2, 3, the second set 2 and 4, the third set 3 and 4, and then the fourth set 4 and 5. We can cover all of U in this example by including all subsets. However, the smallest number of subsets with the complete or the maximum coverage is, in this case, the set 1, 2, and 3, and the set 4 and 5. As you can see, this completely covers all elements in the universe, and it only uses 2 instead of the 4 subsets. Why do we need to find an approximate solution in the first place? So a brute force approach would take big O of m times 2 to the n iterations to find the exact solution. And realistically, that would take too much time for any use to come out of that algorithm. So while many advances in heuristics and algorithms have been made, none has ever managed to solve an NP-complete problem completely and efficiently. And doing so would require that P is equal to NP, and would carry the additional ramification that the global optimums for all NP-complete problems are discoverable in deterministic polynomial time. And currently we don't know whether this will ever be possible, and so in this research we largely focus on heuristic approaches for approximating a solution efficiently, and specifically we're going to be looking at the hybrid genetic algorithm, which is enhanced with wisdom of artificial crowds. So now let's talk a little bit about the approach. And the first portion of the approach that we're going to be taking is running a genetic algorithm, or several populations of genetic algorithms, which we'll talk about later. And here you can see that we just have the general cycle for any sort of genetic algorithm, with you would have the additional arrow of the initialization going before the selection going into that circuit, and then also after convergence you would typically see whether the stopping criteria has been met. But here you can basically see the overall cycle that a genetic algorithm will take, and we'll talk about more of the specifics of the approach that I took in this research in the coming slides. The first step of our approach to the genetic algorithms is to create the initial population. And so for this, the most important thing is how are you going to represent the solutions as a chromosome. And for this I took the typical approach of just using a binary list where the 1 indicates that a subset in the collection should be included in the proposed solution, and a 0 indicates that a subset should not be included in the proposed solution. And over on the right, you see a representation of going between the binary representation and the set inclusion representation, as I call it. So you can see that for the first two elements in the list, they're both zeros and they don't get included at all, and they're just represented as zeros in the set inclusion representation. Then for the third and fifth and sixth elements in this list, you can also see that those are all represented as ones, meaning that they should be included in the proposed solution. And so in the set inclusion representation, as I have it listed, you can see that they've been converted into the actual subsets so that we can more efficiently see what those elements actually are instead of reading them as binary and converting them at the time of testing their fitness. So these are randomly generated binary lists with equal lengths to the number of subsets in the instance, so that we can tell if each subset in the instance is actually included or not. Then we replace the ones with the elements of the indicated subset based on their position as an index in the binary string, which corresponds to an index in the set of subsets. After we create the initial population, the algorithm begins to iterate through starting at the fitness function. And here, every unique element in each included subset is combined into a dictionary to save on processing. The remaining elements in the universe are then counted by subtracting the length of the resulting list for the length of the universe. The total number of subsets used are also counted, since we need to know that as well. The fitness for this problem cannot be determined by only one indicator, as we are looking to minimize both the number of uncovered elements in the universe and to minimize the number of subsets used. Before we continue on to the next function, let's look a little bit at how fitness can function with dual indicators, as we talked about in the previous fitness function. So to accommodate two fitness indicators, the chromosomes are sorted first based on the smallest number of uncovered elements. And we do this because the indicator is selected first, as it is more important. It is the more important of the two indicators in the problem. We would rather have a better coverage than a smaller number of subsets used. So the chromosomes are sorted secondly based on the smallest number of subsets used. And according to this sorting, chromosomes are then that are towards the beginning of the sorted list are more likely to pass on their fitter chromosomes to the next generation. Here I included a short example of how this sortation would look if we were to look at it as a table for the two indicators. So in the first column there you see I have the chromosome number, and this is by original position in the population list, which is really arbitrary. So you can see that we have first, after our sorting, we have the second element from the population, the eighth element, first element, and so on down to the sixth element. And then in the second column, we have the number of uncovered elements in the universe. And this, you can see, is sorted completely, going from the smallest number of uncovered elements up to the largest number of elements. And this is what we want to sort based on first, because it's more important to our solution that we cover all elements in the universe. Otherwise, we could just say that we have 0 subsets used and we have a maximum number of elements in the universe, and that really doesn't tell us anything useful at all. So you can see here we have 83 going to 86, 87, we have several 88s in a row, and then going all the way up to 90 uncovered elements in the universe. In the third column, we have the number of subsets that we used for each of those chromosomes, and the number of uncovered elements as well. And here you can see that it's not an exact sorting from the smallest to largest. We'd have several variations in that because we're sorting based on the number of uncovered elements first. So here you can see that for 83 we have 296 subsets used, and then for 86 we have 298 subsets used. When we get down to the 80s, you can really see how the secondary sorting starts to take effect. And for 88 we have 299 subsets used, the first 88 I should say, and then it goes up to 302 for two different chromosomes, and then all the way up to 303. So you can see that we would select the chromosome number 3 in the initial population first because it has a low number of uncovered elements and a lower number of subsets used as compared to chromosome 5 in the initial population, where we have 88 and 303 subsets used. After we conclude with our fitness function, we can continue on to the mating function. And here, the number of chromosomes that should mate are determined as a certain percentage of the population size. And for these experiments, the mating percentage was set at a constant 50%. Elitism in the population is partially instituted by pairing off the top two performers. And then the remaining chromosomes in the 50% to be mated are then randomly paired together as well. After our mating function, we can continue on with the reproduction process by going to the crossover function. Now here, the list of paired mates that we created is sent to a two-point crossover function where two indices within the range of the length of the chromosomes genes are generated randomly. On the first run of the crossover function, the first parent donates the first and third sections of its genes, while the second parent contributes the middle second portion between the two randomly generated split points. On the second iteration, the second parent donates the first and third sections, and the first parent donates the middle section. The two newly created chromosomes then overwrite the two least fit chromosomes in the population that have not yet been overwritten, since we don't want to overwrite the same two chromosomes each time. That would be pointless. Now here, the process kills off the worst 50% of the original population and maintains the better 50% while introducing new genetic material into the population to help it achieve a better solution. After the crossover function concludes, we continue on to the mutation function. This wraps up our reproduction cycle. And here, to encourage diversity in this research, there is a 10% chance that a mutation will occur in each chromosome for the standard genetic algorithm, which we'll cover a little bit later, and a 1% chance that a mutation will occur for the genetic algorithm with the wisdom of artificial crowds enhancement. And these numbers were experimentally determined to improve the results for each. So if a mutation does occur, it is randomly determined whether it will include 1 to 10 mutations in the actual genetic material for each chromosome that it's determined a mutation will occur. So that number of genes is then randomly selected, and their binary inclusion or exclusion in the list is then flipped. Here I included a visual representation of how that mutation looks with the binary representation of the list and also that set inclusion representation that we looked at before. So here you can see that the mutation indices, which determine where the mutations occur inside of the list, are 0 and 2. So when we look at our first binary representation, we have a 0 in that first slot of our list. And since we have the mutation indice of 0, we want to flip that binary inclusion to a 1, as you can see below with that arrow pointing down. And then that also affects our set inclusion representation by including the set that is also stored in the original problem instance. And we see that that subset is 1 and 3. And then, so for our second indice that we have, which is 2 in the list, we originally have a inclusion there. We have a 1 in the binary representation. So what we do there is we take that 1 and we flip it to a binary 0, and that affects our set inclusion representation by removing that subset of 1, 4, and 5, and we just indicate that it's not included by holding a 0 in that position instead. Our last step for the genetic algorithm is to evaluate the stopping criteria. So after the mutation procedure concludes, the stopping criteria is evaluated to determine if another generation should be processed. The iteration through new generations stops when there has not been a new optimum fitness found in a given number of generations. In these experiments, the number of generations that can pass without any change is set to 100 generations for the standard algorithm and 15 for the genetic algorithm with wisdom of artificial crowds enhancement. The stopping criteria is so strict for the genetic algorithm within wisdom of artificial crowds enhancement to take advantage of the fact that the genetic algorithms make more rapid progress towards finding solutions at the beginning of their run. And then as generations progress, the biggest optimizations are quickly found and selected for, and while the smaller optimizations tend to be found later in the run, and that makes them more costly in terms of time. So multiple populations are also run to cover a larger portion of the search space, introducing greater genetic diversity into the crowd, and while also keeping total runtime relatively low. And that's for just the genetic algorithm with wisdom of crowds enhancement. For the wisdom of artificial crowds enhanced algorithm, we then continue on to the crowd creation process. So from the final generation of each population that was run, the opinions are polled to form the crowd after the stopping criteria has been met. And only the most fit 50% of the population which would have been used to mate if the algorithm had continued are considered as candidates for the crowd. The opinions of whether a chromosome should be included in the final solution are stored in a list of the same length as the number of subsets in the problem instance, which is initialized with zeros. Position in this list is used to indicate which subset in the set of subsets is being referenced. Every chromosome in the fitter 50% of the population has its genes iterated through, and if a gene is included by that chromosome, the value in that corresponding position of the crowd is incremented by 1. So by this method, we can count how often every subset is selected for across multiple populations without storing the resulting chromosomes beyond the termination of each population, and by that we are saving space. Once a crowd is created, we can continue on to the aggregation of the opinions. So aggregation is performed under the assumption that the best subsets to include will be selected for and included most often. After all the populations have been processed and fully and their opinions stored into the crowd's list, the opinions are combined. This combination is done by iterating through each element of the crowd list. If the inclusion indicator, which is just a list element, shows that at or above a certain percentage of the polled population agrees that a subset should be included, then that element or that subset is included in the final opinion of the crowd. The crowd agreement percentage was experimentally set to require an 85% consensus on a subset for it to be included in the aggregated solution. After all the opinions of the crowd have been aggregated, we continue on with the post-processing step of a greedy local search. So here the minimum number of uncovered universe elements is found by checking the fitness of a solution that includes every subset. If there is a larger number of non-included elements than the globally minimum number of elements that was calculated previously, all universe elements that are not included in the aggregation solution are then iterated through. And for each non-included element, all subsets that include that element are found. If none are found, then the next non-included element is analyzed. The subset with the most elements in it is then selected to be added to the aggregation, as it has the highest chance of including another non-included element above just the single element that is clearly being added. The fitness in non-included elements are then recalculated based off the updated aggregated solution until the previously calculated number of uncovered universe elements is reached. Now that we've covered the approach to this research, we can talk a little bit about the results, starting with the data and how it was created. So here the universe for the data set was generated sequentially from 1 to the desired size of the universe in steps of 1. And a determined number of subsets were then randomly generated, each with a number of elements between 1 and 15. The elements inside of these sets are randomly selected so that they are only comprised of elements that are contained within the range of the universe. The combination of the universe and the set of subsets are then written to a text file and saved for consistent testing on the same dataset. And here at the top you can see that I've included that the universe size, just for this example of data, is set to 1000. So that would mean that the universe includes elements from 1 incrementally all the way up to 1000. And here for this example, the number of subsets is set to 5. So our set of subsets, you can see that there are 5 different sets inside of that set. Here's just an example of what that data file would look like when it's stored into that text file. So here you can see that the first row is stored here as the universe, and that incrementally goes from 1 up to 19, and actually above that is just cut off the screen. And then we have, it looks like 10 different subsets included in this certain problem instance, which is saved in the text file. And the data is organized with that first row being the universe, and all following rows are each subset in the problem. And those are just parsed into the program. Now we can talk about the first experiment that I performed regarding the standard algorithm versus the genetic algorithm that was enhanced with wisdom of artificial crowds. So to analyze the wisdom of artificial crowd enhanced algorithms runtime in comparison to the standard genetic algorithm, I ran the same data set of 3,000 universe elements and 1,500 subsets 6 times for the wisdom of artificial crowds enhanced genetic algorithm, which I often denote by GA plus WOAC, and I also ran it 6 times for the standard genetic algorithm. So up here on the left you see the first table, and that's the results of the standard genetic algorithm performance. So you see in the first column we have the run number, just 1 up to 6, and then at the bottom the average of all those runs. In the second column we have the number of uncovered elements, which here you can see that the standard genetic algorithm always was able to find the correct number of uncovered elements, which was the minimum of 38. We didn't have a complete cover for this problem. And then the third column we have the number of sets that were included in each run, and here you can see that the first run there were 666 sets included, the second run 653, so it changes each time since the standard genetic algorithm is built on randomness to a certain degree. And then you can see it down at the bottom that our average performance of sets included was 658.5. And we'll compare that to our wisdom of crowds performance in a second. So the time taken for each of these runs, our average was 1,471.654 seconds. So that's a really long time. And then the time to reach the same answer that the genetic algorithm plus wisdom of crowds approach, looking at that time, you can see that some of them never even reached the average that we have over in our right table, which we'll talk about in a second. And then for the 4 out of the 6 that did manage to reach and surpass that average, they tended to be quite a bit longer in reaching that, almost twice as long in reaching that same solution. So then our second table, we have the genetic algorithm with the wisdom of artificial crowds enhancement. And here in the first column you see that we again have the different run numbers and the average down at the bottom. Second column we have the number of uncovered elements, which again the algorithm always was able to find the minimum number of uncovered elements, which was 38 for this particular instance that we were testing over. And the number of sets included, we actually have a little bit higher average of sets included than the standard genetic algorithm performance. But if we look at that in regards to how much time it took to find that solution, the time is about 350% less than the time that the standard genetic algorithm took to find a similar solution. Here on the left I just have the graphics that are created by the actual program running here. And so you can see down at the bottom in the black we have the actual curve of that the standard genetic algorithm follows to optimize the number of uncovered elements. And then up at the top in the darker, the gray, we have the number of sets used, which is stacked on top of the uncovered elements. So overall, you can see that we have this downward, kind of aligned, but it's really two curves, kind of logarithmic curves going down that are optimizing over the time. And then on the right, we have the standard genetic algorithm performance, and we have that compared to the performance of the genetic algorithm with wisdom of artificial crowds enhancement. So here with the dotted line, you can see the number of sets that are included actually increase for a little bit as the number of uncovered elements decrease initially. up until about time mark 397 and 456, we see that number of sets included increase, and then after that, when the number of uncovered elements gets low enough, we start to see that decrease in conjunction with the number of uncovered elements. And here around time mark 662, between that and 586, we have the point in which the wisdom of artificial crowds enhanced genetic algorithm average optimum is found. So that's a little bit less than half of the way through, actually a good bit less than half, about a third of the way through the standard genetic algorithm run. We find the solution with our enhanced algorithm. And then over where we have that dashed and dotted line, down at the right side of our graph, we have the standard genetic algorithm matches what the wisdom of artificial crowds optimum does at almost 3 times the time. So after seeing the results of this first experiment, I went on and conducted a second experiment. And for this one, my goal was to improve the results of the accuracy that the genetic algorithm plus the wisdom of artificial crowds algorithm provided. So in the second experiment, I allowed each of the 4 populations to run for a longer period. And in allowing the populations to run for a longer period, it should increase their agreement on the best sets to include, which should also in turn provide a better starting point for the post-processing local search. And to increase the runtime for each genetic algorithm, the stopping criteria, which is the maximum number of generations that can pass without an improvement, was raised from 15 generations up to 100 generations, which actually matches what we did with our previous experiment in the standard genetic algorithm. Here we can see the genetic algorithm plus wisdom of artificial crowds increased runtime results. So in the first column you can see the run number, and then down at the bottom the average for all of these 6 runs. So again, we managed to find the optimum number of uncovered elements with each run, which was 38. We used the same data set. And then for the number of sets included, you can see that our average dropped down to 609.83 sets included. And our time is quite a bit more than the previous algorithms that we've tested at 5,490.335 seconds. So let's go over a couple conclusions that we can draw from experiment 1. So the results of this experiment show that on average, a 325% saving in total runtime is observed when using the Wisdom of Artificial Crowds enhanced genetic algorithm as compared to the standard genetic algorithm. And in the 4 runs of the standard genetic algorithms that managed to find the optimal solution, or optimal number of uncovered elements, which was 38, and still surpasses the genetic algorithm plus Wisdom of Artificial Crowds optimization of the total number of sets used, the standard genetic algorithm on average still takes 274% longer to arrive at an equivalent answer to the genetic algorithm plus Wisdom of Artificial Crowds approach. So both the standard genetic algorithm and the genetic algorithm plus wisdom of artificial crowds approaches always manage to fully optimize the number of uncovered elements. But the standard genetic algorithm tended to have a 0.7% smaller number of included sets when its stopping criteria of 100 generations with no change was met. However, the genetic algorithm with Wisdom of Artificial Crowds enhancement was also 25% more reliable in providing solutions in the same range. Continuing on, this should say Experiment 2 conclusions, but let's talk a little bit about those. The improved results from each population resulted in an 8% reduction in the average number of subsets included in the optimum solution. And the best solution that was found had just over 606 subsets included to cover all but the optimal 38 elements in the universe. The average time for this method to provide an optimum solution on average took 3.7 times that of the standard genetic algorithm and over 12 times that of the genetic algorithm plus wisdom of artificial crowds approach with the shorter runtime for each population. So this results in a runtime of just over 1.5 hours. So overall, what can we draw from these 2 experiments? So the genetic algorithm plus wisdom of artificial crowds method is preferable to the standard genetic algorithm for large data sets as it arrives at a good approximation for the set cover problem more quickly. This is because the genetic algorithm with wisdom of artificial crowds method can take advantage of the rapid improvement that a genetic algorithm makes at the beginning of its run while not compromising the accuracy. Allowing for multiple populations, the genetic algorithm with wisdom of artificial crowds can explore a larger portion of the search space. Inconsistencies between the populations are then edited out, and the local search has a better starting point to make a viable and accurate solution. The solution can also be made more accurate by increasing the total run time, although there's a very large trade off between time and accuracy. In most applications, the 8% increase that we observed in accuracy is not worth the large increase in processing time. However, for less time sensitive optimization instances, this may be a viable approach. Thank you all for taking the time to watch this presentation on the set cover problem with the genetic algorithm plus wisdom of artificial crowds approach. Let me know if you have any questions about anything that I've talked about in here, and thank you all, and I hope you all have a great break.